Minimum spanning tree is one of the important part in design analysis of algorithm. Minimum spanning tree has a graph representation using G is equal to VE, whereas this graph is represented as we regularly do. Then we have W, U, V. So U and V are the vertices, with E is the number of edges connected to that. W is the weight which represents the connectivity between U and V. This weight can represent the distance from U to V, or temperature, or speed, or money, anything. According to the problem statement, we do have different weights or its representation in the graph. Minimum spanning tree is generally defined the total cost of traversal of all the vertices in the minimum spanning tree. So all these vertices, when they are connected in the graph, we will choose the set of edges which are really connected, or which allows us to connect it to almost all the vertices. So the total connectivity, or total number of weights which are connecting to each and every vertex, is defined as a total weight of the minimum spanning tree. So total weight of the minimum spanning tree is the edges which are selected connecting to all the vertices. The total value of the weights is known as the value of minimum spanning tree. Further, the traversal of the graph, or we say that for finding out minimum spanning tree, we have two algorithms in use: Prim's algorithm and Kruskal's algorithm. This is a representation, a small example of minimum spanning tree. So we have nodes A, B, C, D, E, F, G, H and I. So all these nodes or vertices are connected to each other with the edges. The weight represent here is the connectivity between the vertices A and B is connected with the edge, and 4 is the weight of this particular edge, whereas B and C is connected with the edge, the weight is 8. C and D is connected with the edge and its weight is 7. Accordingly, C and I is connected with the edge of weight 2. So this is how the minimum spanning tree is. The graph is. But we have darkened some of the vertices here, some of the edges here. So this is A to B, B to C, C to D, D to E, C to F, C to I, and F to G, G to H. So only these edges are selected. These are shaded in a gray to represent that these are the most valuable edges which we allow us to note or to count in the minimum spanning tree. So if we select only these edges, then we will be able to traverse or visit almost all the vertices in this particular graph. That is why the selected or darkened gray shaded edges is a part of minimum spanning tree. So minimum spanning tree for this particular graph is shaded edges. So as we said, we have two algorithms to use for minimum spanning tree. The first one is Kruskal's, other one is Prim's algorithm. We'll try to learn Kruskal's algorithm here. The method to find a minimum spanning tree. This is one of the most popular algorithm used to find a minimum spanning tree. This is a greedy method. This uses greedy method. Always find a light minimum edge. As and when the algorithm starts, it will always choose a minimum or light weighted edge. The edge which has the minimum weight will be selected first. So for this, we need to sort almost all the edges available in the graph, so that we will get an opportunity to connect to all, or to have all the edges connected to each other. So when we sort all the edges, we'll get sorted edges in ascending order. The first edge in the sorted list will be the minimum edge. So we'll choose that first, then the second, then third. The forest include multiple trees. So we will be having a understanding of this Kruskal's algorithm is in the form of trees, and the forest. So we have in the initial stage we'll consider almost all the nodes are disconnected with each other, and every node will represent a tree. So when we try to connect these trees to each other, then we will have the connectivity as a forest. So connecting two trees in the forest is a key solution. Light edge is selected to connect the trees. Applications. There are a number of applications of Kruskal's algorithm. Before we start understanding Kruskal's algorithm, let's have a look on this. The network for roads and rail tracks connecting all the cities will use a Kruskal's algorithm. Irrigation channel. So the fields where we will be transporting or providing the water supply will also use the Kruskal's algorithm for the best outcome. Designing a fiber optic grid on or ICs will also use a Kruskal's algorithm. Traveling salesman problem is one of the most popular problem used or solved using Kruskal's algorithm. Then we have cluster analysis, pathfinding algorithms using AI and game development. These are some of the areas where Kruskal's algorithm will be used. This is the algorithm. Kruskal minimum spanning tree will get an input as a graph and the number of weights of all the edges. First of all, we will initialize a set A with empty. Nothing is available in this particular set A. For each vertex which is a part of this particular graph, almost all the vertices will mark as a set V. So every individual vertex is considered as a tree, as I said in the last slide. So all the vertices are considered independent, not connected to each other. It's the first stage. Second stage, we'll sort these edges into a decreasing order, non-decreasing order, increasing order by weight, by its weight. So the edges, as we have defined in this particular diagram, all these edges A, B, B, C, C, D, D, E and C, F, almost all these edges are sorted as per their weights. Once we sort them, first for each edge UV, we'll select the first edge taken in a non-decreasing order. The lightest edge will be selected, and that particular edge we will find whether this particular set U and set V are the two independent vertices initially. If those are still not connected with any other edge, then we will choose this edge as a part of the final solution and will include it in a set A, and then we connect U and V all together. So what we have to do, choose the lightest edge, check whether this U and V, the vertices of this edge, are connected with some other edge. If yes, then neglect it. If no, if they are not used or not connected to the graph, then we will choose it and will include it into the final solution and combine them or add them in the solution, and the result is A. So this is how the Kruskal's algorithm works. The understanding of this Kruskal algorithm is explained here. This is the first A is a graph, a forest where all these vertices are independent, not connected to each other. So we'll disconnect them, we'll consider them as not connected. Then we'll arrange in a increasing order of all these ages. The weights are here: 4, 8, 7, 9, 14, 10, 2, 4, 6, 2, 7, 8 and 1. If we arrange all these ages in an increasing order, so we'll get the lightest age as a 1. So this lightest age is 1. That is why we'll check whether this particular H and G of this particular age is connected somewhere. Is G connected to F? No. H is connected to I and A initially? No. That is why we'll choose this age H and G as a 1. Then once we do it, now we have this age included in a minimum spanning tree. Once after that, after 1, the lightest age we have is Ci and Gf. Either of these will be selected. Let's consider this particular Ci. Once we consider Ci with the lightest weight age is 2. So we'll check whether this I and C are connected anywhere right now. No, because initially we said all the vertices are independent, not connected to each other. So this is selected. So we have chosen this particular HG and CI as a part of minimum spanning tree. Third lightest weight, after this we are going to choose GF. Once we choose GF, we'll check whether this G and F are connected. Yes, G is already connected, but F is not connected. F is not connected anywhere. G is connected to H. Already we have done it. But since G and F is not connected, so we have to connect F, then we will connect this. Done. The next lightest edge we can get is AB and CF. So can select either of these, no problem. We'll go with AB. So AB is selected and A and B both are not connected anywhere to any other vertex. So both these vertices are considered. So this is 4. Then the next shortest, see, every time when we are choosing the edge which is in ascending, already set in a ascending order, that is why one after another it is easier to select, and this is what a greedy pattern is. So C and F is the next edge we select. So the C and F we have here 4. This is considered. Since C and F was not connected, so we will choose this and we'll add it into that. Then we'll go with this 7 weight. C and D is not connected, so we'll choose this and go with that. So we have a 7, the next 7, but I is already connected with C and H is connected with G, so there is no use of connecting this thing. That is why we'll neglect it. The next part is choose. Once we have done with 7, we'll go with the 8, weight of 8. So this A and H is not connected previously, so we'll connect and consider this particular edge. So we have another 8 in the order. So B and C. B is already traversed and connected to A. C is already connected with number of vertices. So B and C both are already connected, so we'll not choose this. Then we'll go with the 9. D and E. E is not connected anywhere previously, so we'll connect it and consider 9. Then we'll go for connecting 10, but 10 is already connected. E is connected with D and C is connected with F. Then there is no point in connecting these two. So then the last edge is 14. So D and F, which is connected to D and F. D is already connected, F is already connected. So we'll not consider this particular edge for minimum spanning tree. So the edges we count in the minimum spanning tree are AB, AH, IC, CF, CD, DE and FG, and the final is GH. So the count of this 1 plus 2 plus 4 plus 2 plus 8 plus 4 plus 7 plus 9 is the total weight of minimum spanning tree. So there can be a question, what is the cost of minimum spanning tree in the examination? So the count of the count of all the weights included in a minimum spanning tree is known as the cost of minimum spanning tree. Particular connectivity from I to G is not higher than is not having a higher. That is why we will go with this particular connectivity like C to F. C to F is having 4. So we have chosen the weight C2I, that is 2, and after that we'll move in the next part. So among the available all the ages, see this E8 and 11 and E8 and 7, we have got C2F as a minimum, so we'll choose from C2F, that is 4. So once we go, we have F as a new vertex which has been collected from the Q. So all the among the available ages, 2 is having the minimum weight. So connect from F to G. From G, now G is again a new, and from among the available vertices, or sorry, the ages, the weight of this G to H is a minimum. Then this one is selected. Then we have got a new vertex, that is D, and among available vertices we have got 7 as the minimum weight, so we'll choose this. We can have a connectivity from I to H, but this will form a cycle, and cycle is not allowed in the vertices, and these vertex are already visited. So C to D is formed since D is now connected to C, and in the remaining vertex we have to extract. E is the last vertex which is remaining, so we'll extract it, and among the available connectivity, so we have got the minimum D to E as a weight 9. Again, the connectivity between all the addition of the weights and the connectivity between all the vertices is known as the minimum spanning tree, and this is how the Prim's algorithm works.